Welcome to Graph, Homomorphisms and Universal Algebra video session number 5. Previously we have seen how polymorphisms can be used to show that certain algorithms can be used to solve the constraint satisfaction problem for a given digraph H in polynomial time. For example, we have seen that totally symmetric polymorphisms characterize when the arc consistency procedure can be used to solve a CSP. And we have seen majority polymorphisms and how they can be used to prove that the path consistency procedure is correct. Today we'll turn this around. We'll start with a very nice property that a polymorphism can have, and we'll ask which digraphs have this polymorphism. And the nice identities we'll pick out are called Maltsev identities. In the previous video session we have introduced majority operations. These are ternary operations that return x if at least two of the arguments are x. How about minority operations? So here we have the identities f of x xy equals f of x y x equals f of y x x equals y. It turns out that for digraphs, having such polymorphisms is a very strong property, already if we drop the middle term from the above identities. An operation satisfying these identities without the middle term is called a Maltsev operation. To motivate why one might want to drop the middle term, let's look at a group G, additively notated. Then the map that sends the triple x, y, z to x minus y plus z satisfies the Maltsev identities, as one can easily check. Today we'll be interested in digraphs that have a Maltsev operation as a polymorphism. Let's have a look at an example. We choose the group Z5. I claim that the Maltsev operation x minus y plus z is a polymorphism of the directed cycle of length 5. Luckily, the vertices of C5 are just the group elements of Z5, namely 0, 1 up to 4. Let's call the Maltsev operation M, and we have to check that M preserves the edges of C5. So we pick edges x, x prime, y, y prime, and z, z prime, and we look what M does with the edges. To be an edge means to be one apart modulo 5. So here we can just do a simple calculation to see that the function values of M are again 1 apart modulo 5. And that's the example. A directed graph H is called rectangular if for all edges xy, x prime y, x prime y prime of H, I prefer them to be drawn like this, we have that the pair x, y prime is also an edge of H. So in the specific situation of the picture, we have some sort of shortcut edges. Now observe the following fact. If H has a Maltsev polymorphism, then H must be rectangular. And this is obvious. We simply apply M to the three edges. There will be one argument which is repeated, and this argument is ignored, it cancels out, and the polymorphism condition then gives us the shortcut edge. The name rectangularity comes from drawing the edges in a different way, namely like that. The converse is not true. There are graphs that are rectangular but do not have a Maltsev polymorphism. A small example is the following digraph drawn on the right. It has 3 vertices and 2 loops and altogether 4 edges. It can be checked exhaustively that the graph is rectangular. That's relatively straightforward but boring. To see that it does not have a Maltsev polymorphism M, let's see what such an operation M would do with the edges AA, BC and CC. The endpoints would be mapped to A because of the Maltsev identity. For the start points, well, we are talking here about an arbitrary Maltsev polymorphism, so we don't really know where they are mapped to. But let's pick another 3 edges, AA, AB and CC. This time we know where the start points are mapped to, namely to C. But now we are in trouble, because in our graph there is no vertex which has an edge to A and from C. So we conclude this graph has no Maltsev polymorphism, but it's rectangular. So if we want a necessary and sufficient condition for the existence of a Maltsev polymorphism, we need a stronger property than rectangularity. A finite digraph H is called k-rectangular if it satisfies the rectangularity condition, but where edges are replaced by directed paths of length k. A graph which is k-rectangular for all k is called totally rectangular. One can show by induction, and by a similar argument as we have seen it for rectangularity, that a directed graph H with a Maltsev polymorphism must be totally rectangular. What can we do with total rectangularity? We can say something about orientations of cycles and directed cycles. The net length of an orientation of a cycle is the value that you obtain if you traverse the cycle, and you compute +1 if you pass through a forward edge, and you compute -1 if you pass through a backwards edge. When you then return to the vertex you started at, you look at the value you obtained, and this value is called the net length of the cycle. In the example, we have net length 2. The directed cycle CK has net length k. We'll now prove the following lemma. If G is totally rectangular and has a cycle of net length d, at least 1, then G contains a directed cycle of length d. To prove this lemma, let C be a cycle of net length d, and we'll prove the statement by induction on the length of the cycle. Note that any cycle can be decomposed into maximal directed paths. In my picture, this is nicely visible from the way in which I have drawn my cycle. If this decomposition has only one part, we have found our directed cycle and we are happy. Otherwise, let P be the shortest directed path in the decomposition. Let Q be the directed path that comes before, and Q prime the directed path that comes after in the decomposition. Then we can apply the length of P rectangularity and obtain a shortcut path. So we find a shorter cycle, which again has net length d, and the statement follows by the inductive assumption. Now comes the main theorem of today's video session. It is basically a not so old result of Kazda in a refined form from a paper of Carvalho, Egri, Jackson and Niven. Let G be a finite directed graph. Then the following are equivalent. 1. G has a Maltsev polymorphism. Of course, this is the topic of today. 2. G is totally rectangular. And the implication from 1 to 2 is what we've already seen. 3. If you're interested in graphs up to homomorphic equivalence, what follows is the most concrete description. We have a case distinction. Either G is acyclic. In this case, the core of G is a simple directed path. Otherwise, the core of G is a disjoint union of directed cycles. Note that this shows in particular that CSP of G can be solved in polynomial time. This is because the CSP for directed paths and for directed cycles is in P, can be solved by the path consistency procedure. Also note that both directed paths and directed cycles also have a majority polymorphism. So it seems that maybe also G has a majority polymorphism. But note that this requires proof. The fact that the core of a graph has a majority polymorphism does not imply that the original graph has a majority polymorphism. So somehow the fourth item of our theorem here comes as a surprise. Indeed, it can be shown that G has a majority, and even a minority polymorphism. We will prove that 2 implies 3. The proof that 3 implies 4 we will skip. You can find it in the paper of Carvalho, Egri, Jackson and Niven if you're interested. The implication from 4 to 1 is trivial. This is what we'll prove after the break. 2 implies 3 comes after the break, which is today a Corona stay-at-home bread break. Bake bread break. Let's now prove the interesting direction 2 implies 3 of the theorem. Let G be a finite, totally rectangular, directed graph. We have to prove that G is either homomorphically equivalent to a directed path or to a disjoint union of directed cycles. Note that in the proof we may assume that G is connected, because if it is not connected, we can prove the statement for each connected component of G separately, and then also get the result for all of G. In the proof, we first suppose that G has a homomorphism to a directed path, Pn. Pick n smallest possible. Let U be a vertex of G that is mapped to 0, to the element 0 of the path. And let V be a vertex that is mapped to the vertex n in the path. Clearly such vertices must exist, because if we didn't use 0 or n with our homomorphism, we could have chosen a shorter path in contradiction to our minimal choice of n. Since G is connected, there exists a path from U to V, and this path also homomorphically maps to Pn and therefore has net length n. We use the same definition of net length as for orientations of cycles. The path need not be directed, but using total rectangularity and a simple induction, we can also find a directed path of net length n from U to V. And this shows that Pn homomorphically maps back to G, because we can map Pn to this path between U and V. This concludes the proof that G and Pn are homomorphically equivalent. So in the following, we have to treat the case that G does not homomorphically map to Pn. Here are 2 simple but useful dualities. We will not prove them here, but they are easy exercises that I recommend writing down. The first is that a graph G does not homomorphically map to a directed path if and only if G contains an orientation of a cycle of net length strictly larger than 0. The second duality describes which graphs do not homomorphically map to Tn, the transitive tournament. This is precisely the case if G contains a directed cycle. If the first condition does not apply, G is called balanced. If the second condition does not apply, G is called acyclic. And there's yet another observation I forgot. A finite digraph does not homomorphically map to a directed cycle if and only if G contains an orientation of a cycle whose net length is not a multiple of n. Again, this is easy and an exercise, but we'll use it in the following. Here comes the final piece of the proof of the theorem. We have to treat the situation that G does not homomorphically map to Pn. By our first observation, G contains an unbalanced cycle. Total rectangularity and the lemma from before the break imply that G also contains a directed cycle, Cn. Choose n smallest possible. And suppose for contradiction that G contains an orientation of a cycle whose net length d is not a multiple of n. I claim that we may assume that d is strictly smaller than n. Why? Well, G is connected. So there is some path between the cycles. Recall that we are not talking about simple cycles. Vertices on our cycles might be repeated. So we can look at the cycle which traverses the cycle of net length d, then goes to the directed cycle, goes forward or backwards on the directed cycle as many times as we want, and then returns to the start point. By appropriately choosing the number of times that we traverse the directed cycle, we can make sure that the net length of the newly created cycle is larger than 0, but strictly smaller than n. This proves the claim. Now we use the total rectangularity assumption in our lemma a second time and derive that G must contain a directed cycle of length d. And this is in contradiction to the minimal choice of n. We found a smaller directed cycle. Hence, every cycle in G has a net length which is a multiple of n. And our third observation therefore implies that G has a homomorphism to Cn. And this concludes the proof. So far in the course we have seen quite a bit of advertisement for polymorphisms. Totally symmetric polymorphisms, majority polymorphisms, and today Maltsev polymorphisms. All of them, they seem to suggest that what really matters is polymorphisms. In the next lecture we'll take the first abstraction leap in the course. There will be 2 more abstraction leaps. And this abstraction leap is that we will pass from studying digraphs to studying the set of all polymorphisms of the digraph. And we'll understand completely what we lose from taking this step. What do we forget about the digraph when we only know the polymorphisms of the digraph? It turns out that actually we don't lose so much. Okay, so take care. Until soon.